Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Today we'll be doing chemical properties of alcohols. So alcohols can act as nucleophiles as well as electrophiles in their reactions. So when they act as nucleophiles when the bond between oxygen and hydrogen is broken. For example, when it's acting as a nucleophile, alcohol will react with an electrophile. For example, this carbocation. So the lone pair of electrons on oxygen atom will be attracted towards the positive charge on carbocation, and as a result a bond is formed. There's a positive charge on oxygen atom as a result, and then in the next step the hydrogen will move away as proton. The bond is formed, proton is given, and in this reaction alcohol is acting as a nucleophile. It's seeking a positive center. Alcohols will act as electrophiles when reaction occurs in presence of acids. So in presence of acids, the proton given by the acid will react with the lone pair of electrons. Protonated alcohol acts as electrophile and reacts with nucleophiles such as bromide ions. Now, electrons from bromide ions move towards the carbon atom when this protonated OH2 part with a positive charge will take the electrons and move away as water. So a BrCH2R is formed as a result. So here the alcohol is behaving as an electrophile after protonation. Reactions of alcohols can be classified into these types depending upon the point of cleavage of alcohol. If the cleavage is between oxygen and hydrogen, then the reactions will be categorized as reactions involving cleavage of oxygen-hydrogen bond. Then bond may break between carbon and oxygen part also. These are reactions involving cleavage of carbon-oxygen bond. And third category is where both the alkyl groups and the hydroxyl groups are involved. Let us study in detail the first category, reactions involving the cleavage of oxygen-hydrogen bond. Reactions with active metals, acidic character. So alcohol will react with active metals such as sodium, potassium, magnesium, aluminium to give hydrogen gas and metal alkoxide as a result. So for example, with sodium, ethanol will form, hydrogen will be given as hydrogen gas, and Na and OCH2 CH3 combines to form sodium ethoxide. 2 molecules of sodium ethoxide. Similarly, with magnesium, it will form magnesium ethoxide and hydrogen, and with aluminium, it will form aluminium alkoxide. If tertiary butyl alcohol reacts with aluminium, it will form aluminium tertiary butoxide and hydrogen gas. So here, because alcohol is giving a proton, it's acidic in nature. It is showing acidic character. Alcohol acts as a Bronsted acid because they donate a proton to a strong base. BH will be formed as a result, and alkoxide ion will be formed. Now here, because it's giving a proton, it's acting as an acid, and alcohol minus proton, alkoxide ion, is a conjugate base of alcohol, and because it's a weak acid, its conjugate base is a strong base. So this shows that even water is stronger acid than alcohol. Water is a stronger acid than alcohol. And the base alkoxide ion is a stronger base than hydroxide ion. And why water is a stronger acid? Because if we compare between water and alcohol, the electronegative oxygen atom, it attracts the electrons of the oxygen hydrogen polar bond towards itself, thereby facilitating the release of proton. ये इलेक्ट्रॉन्स इधर आ गए तो H प्लस रिलीज हो जाएगा, तो ये एसिड की तरह एक्ट कर रहा है. अल्कोहल में भी ये होता है, लेकिन ऑक्सीजन की टेंडेंसी टू टेक इलेक्ट्रॉन्स डिक्रीज कर जाती है, क्योंकि एल्काइल ग्रुप्स इंडक्टिव इफेक्ट शो करते हैं और इलेक्ट्रॉन रिलीजिंग इफेक्ट शो करते हैं. इलेक्ट्रॉन्स इधर को जाएंगे तो ऑक्सीजन की इलेक्ट्रॉन्स लेने की टेंडेंसी कम हो जाएगी. So because there is one electron releasing group in alcohol which is not there in water, so water is a stronger acid than alcohol. And if you compare between base, then alkoxide ions are stronger base than hydroxide ion. For example, sodium ethoxide will be a stronger base than sodium hydroxide. Comparison of acidic strength of different types of alcohols. So we see that primary alcohols are more acidic than secondary than tertiary. This is because there is only one electron releasing group that decreases the tendency of oxygen to take electrons in primary alcohols, whereas there are two such groups in secondary alcohols and three groups in tertiary alcohols. So the tendency of oxygen to take electrons is least in tertiary alcohol. So this is the least acidic alcohol. On the other hand, their alkoxides basic strength will follow the reverse order. That is, a tertiary alkoxide will be stronger base than secondary alkoxide than primary alkoxide ion. Alcohols also act as Lewis base because they have a tendency to donate pair of electrons. This is because of the presence of lone pair of electrons on the oxygen atom of alcohols. Reaction with metal hydrides. So alcohol will give a proton and react with sodium. So this H and this H will combine to form hydrogen and sodium alkoxide is formed. Then reaction with carboxylic acids. Alcohol will react with carboxylic acid in presence of concentrated sulfuric acid or hydrogen chloride gas. So alcohol gives H and carboxylic acids give OH to form water and ester is formed. So this reaction is called esterification reaction. For example, acetic acid plus ethyl alcohol will form ester. Because ester is formed, it is an esterification reaction. In this reaction, if HCl gas is used in place of sulfuric acid, then the reaction is called Fischer-Speier esterification reaction. Presence of bulky groups in alcohol or in the acid will decrease the rate of esterification. So, in alcohols, the least bulky group methanol will be more reactive than ethanol, than isopropyl alcohol, than tertiary butyl alcohol. Similarly, in carboxylic acids, formic acid or methanoic acid will be more reactive than acetic or ethanoic acid, than 2-methyl propanoic acid, than 2,3-dimethyl propanoic acid. In reaction with Grignard reagents also, the alcohol gives H to the alkyl part of Grignard reagent RMgX to form alkane RH, R-H, and alkoxy magnesium halide is also formed. Now, the alkane that is formed consists the alkyl group of the Grignard reagent. For example, CH3OH plus C2H5 Mgr will form C2H6 plus methoxy magnesium bromide. So in reaction with Grignard reagent also, alcohol is behaving like an acid. Reaction with acyl chloride or acyl anhydride, and this proton will react with the chlorine of acyl halide or acetate group or carboxylic group of acid anhydride to form ester. So CH3COO CH2CH3. This ester is formed and HCl is formed. So because an acyl group is attached, so reaction is called acylation reaction. When we react an alcohol with acyl halide or acyl anhydride, the reaction is called acylation reaction. So acyl anhydride, when reacts with alcohol, the H of alcohol and acyl group of acyl anhydride will combine to form acid, carboxylic acid, CH3COH, and these two combine to form CH3COO CH2CH3. So reaction is called acylation reaction. The second category of reactions are reactions involving cleavage of carbon-oxygen bond. In these reactions, the order of reactivity of alcohols is tertiary is more reactive than secondary than primary. This is because of the electron releasing inductive effect of the alkyl groups. In case of tertiary alcohol, there are 3 electron releasing groups. So electron releasing group will increase the electron density towards the oxygen. So this carbon OH bond, it becomes more polar and is easier to break. More the number of alkyl groups, more easier this bond can be broken. So a tertiary alkyl group will be more reactive than secondary, will be more reactive than primary alcohol. So we can say that moving from left to right, the reactivity decreases. The reactions where this OH bond is broken, we have these examples. Reaction with hydrogen halide. So alcohol gives OH, HX gives hydrogen, water is formed, and haloalkane is formed. Order of reactivity of hydrogen halides is hydrogen iodide is more reactive than hydrogen bromide is more reactive than hydrogen chloride, because iodide is a better nucleophile than bromide than chloride. And order of reactivity of alcohols, as we have seen above, tertiary is more reactive than secondary, is more reactive than primary. So in case of primary and secondary, which are less reactive, we require some Lewis acid catalyst, whereas in case of tertiary alcohol, no catalyst is needed. So if we react a primary alcohol with hydrogen chloride, we will need the Lewis acid catalyst anhydrous zinc chloride. We have to heat it. So alcohol gives OH, HCl gives H, water is formed, and ethyl chloride is formed, chloroethane. This reaction is known as Grove's process. A secondary alcohol will also react in similar manner. But we don't need this reaction to be heated, because reactivity, order of reactivity increases. Tertiary are more reactive than secondary than primary. In case of tertiary alcohol, even the catalyst is not needed. No heat is needed. At room temperature, the alcohol will react with HCl to form chloroalkane and water. This was with HCl. In case of HBr, a small amount of concentrated sulfuric acid is needed instead of zinc chloride. And for secondary and tertiary, no catalyst are needed. Secondary and tertiary alcohols will undergo dehydration. No bromides will be formed. HBr is generated in C2. HBr is unstable. So what we do is we react the alcohol with KBr and sulfuric acid and produce HBr at site, which is called in situ preparation. So alcohol plus KBr plus sulfuric acid will form water and bromoalkane and KHSO4. This reacts to form HBr. To react HI with alcohol, Again, we will prepare HI in situ. So we react potassium iodide with phosphoric acid to produce HI. This HI reacts with alcohol to produce iodoalkane and water. So Ki plus H3PO4 will also form potassium hydrogen phosphate. Reactions with phosphorus halides. We can react alcohol with halogenating agents such as PCl5, PCl3, PBr3, Pi3. So with PCl5, the reaction occurs. A bond will break from this end and this end. So CH3CH2Cl is one of the products. Then we have POCl3. Then we have HCl. In case of PCl3, 3 molecules of alcohol will react. So OH goes 3 molecules of alcohol will give 3 OH to react with phosphorus to form H3PO3, and 3Cl will come in the place of OH. So 3 molecules of ethyl chloride will be formed along with H3PO3 or POH thrice. It's also called H3PO3. Similarly, with PBr3, 3 molecules of bromoethane and H3PO3 will be formed. With Pi3, 3 molecules of iodoethane and H3PO3 is formed. Now these are unstable, so they are prepared in situ by reaction between phosphorus and bromine, and Pi3 is formed by reaction between phosphorus and iodine. Next is reaction with thionyl chloride. Again, the OH part of alcohol will be given, and the products formed can be understood in this manner. Again, just like PCl5, dissociation occurs. We'll write SOCl2 in this manner, SO in front of O, Cl in front of ethyl, and Cl in front of H. So ethyl chloride and SO2 and HCl are formed. This reaction is preferred because apart from chloroalkane, the other products are gaseous in nature and are removed, and pure haloalkane can be formed. Next is reaction with ammonia. So the OH of alcohol reacts with the H of NH3 to form water. The remaining NH2 combines with ethyl to form ethylamine. This reaction will not stop at this stage. It can further react also to form secondary and tertiary amines. Reaction takes place in presence of alumina at a temperature of 633 Kelvin. Now, this ethylamine which is formed can further react with another alcohol molecule. Again, OH and H will combine to form water, and CH3, CH2, NH, and another CH3, CH2. That means 2 ethyl groups with NH. Similarly, another alcohol molecule and 3 ethyl groups with nitrogen are formed. So we find a mixture of primary amine, secondary amine, and tertiary amine in this reaction. Next category, reaction involving both the cleavage of alkyl and hydroxyl groups, we will take up in our next video. That's all in today's topic. Thank you. Have a nice day.